Welcome to the section on generators. Let's consider a problem in which we want to get the exponents of numbers ranging from, say, 0 to, say, 100,000 or a million. That's 1e6. Or we could even start with a smaller number, like, say, even 10. So if we have to go from 0 to 10, we could define a, which is simply I for I in range 10. Take this way, and that's fine. Now we could print out a, and there we go. We have this list of values ranging from 0 to 9, and then if we want to get the exponent, we have simply to define this function exponent, which takes in a, and then we return a list wherein we have I. We have, let's consider our exponent to be, say, 1.01. So we have 1.01 to the power of a, or rather to the power of I, for I in a. Run that, and then here we go. We have exponent of a. We see we have 1, 1.01, 1.02, and so on and so forth. We could increase this range to, say, 1,000 or even 10,000. There we go. Let's take off this print right here. Okay, now we can go ahead again to increase this. We have an overflow because this number is quite large. Okay, so we see the values we're obtaining. Let's keep increasing. It's actually still loading. Let's interrupt this kernel. Let's run this. Run again. You see, it takes a lot of time to load all this in memory, and it's still loading the data in memory. Let's interrupt again and take a smaller number. Interrupt that. Run again. This time around it took less time. Let's run that. Take some time. There is overflow, so let's reduce the number again. Run again. Takes a while. And that's what we obtain. Now, as we could see, there's a problem with the way we are approaching this. And the problem is that we always have to load all this data in memory before computing this exponents for each element in this list. And given that each of these elements are actually independent, it means we could look for a more efficient way of dealing with this data. By efficient, we mean maybe storing just the part of the list which we'll need for a given time to compute its exponents, and then only computing the exponents whenever needed. Now, apart from this memory problem, the next problem we may face is the fact that in some systems, like in real-time systems where data isn't already packed somewhere, so like if you have data in some database and that you are doing some computation on this data, then it's possible that you could load it up and then go this way. But then in some real life scenarios where this data is not necessarily located in the database, but maybe it's coming in as input streams, in that case we can't actually preload this data because at a given time t, the data at t plus 1 is inexistent. Now, that said, a common solution to this problem is working with generators. Let's see how they work. Now, we have this list right here which has been defined. Now we could actually let's reduce this. Let's go back to 10. Run this again. That's fine. We'll take this one. Let's even maintain it. That's fine. We now redefine a gen exponential, which takes in the number of elements we have. That's 10. So we're taking the maximum number of elements, and then in here we're actually going to return the exponential. Basically is this. So we're going to return this here. But now instead of doing this return, we are going to yield. So with generators we have this yield keyword, and the way it works is very simple. Instead of returning the whole array or the whole list, what we have is that we have this yield such that for every element in my list, so let's take this, let's say this is n, so for every element in my list I'm gonna yield the output, or I'm gonna generate the output. So right here, instead of coming to like define this such that we have the whole list getting into this function, and then this function now returns also this whole list. Now we're defining this function differently, in the sense that we have this maximum number of inputs, and then for each and every one of them, or as they are passed in, we just simply yield the outputs. So run that, and then the way we take these values, or the way we obtain the outputs from this kind of generator function, is by simply using the next keyword. So we have next of gen exponential. What we passed in is, we could take for example 10. Now that's not okay. We have to let's specify g for example. So we have this gen exponential which takes in 10. So now we would say that the maximum number of inputs we're working with is 10, and then we define that as such, and then we now look for the next g. We have this error, int not iterable. Yeah, it should be range. Run again. That's fine. So we see we have this first element, and then if we repeat this, let's repeat this, we'll have the next element. Let's do some prints. Print. See, we have this element, this next, and so on and so forth. Notice that because we had done we had called on this next previously, we ended up having this first value. Instead we're having this value here and this one. So let's rerun this again. We have 1 0, next one. Let's take all this 1 2 3 4. Yeah, run again, and we see that we have this same output right here, but with the difference that this time around the outputs aren't just returned as a whole, but instead they are being generated in batches of 1. We can now go ahead and increase this n. So let's take for example that. There we go. You see that unlike with this, let's take this back here, run it again. You see before it has to load all this in memory. After loading this, we have to get into this. We have to get into this. You see that it's already taking a lot of time. Now let's cut this a bit. Interrupt. See, it takes a while to load this in memory, whereas here it doesn't take that much time to load in memory. See, it practically takes no time and the job is done. So clearly working with generators is memory efficient, and also in some cases, as we said, like when we have continuous flow of data, we can't actually work with data which doesn't exist yet, and in such cases we have to make use of generators like this.